I will be talking about Physics Lab 1 constant velocity. This experiment is a comparison between an experimental model and a computer predicted model exhibiting motion over a period of time in constant velocity. We are interested in constant velocity and the underlying factors that cause this particular form of motion. These underlying factors can be explained using Newton's second law, which takes form in the equation final velocity equals initial velocity plus net force over mass times change in time. For constant velocity to occur, which is understood as final velocity equaling initial velocity, the net force acting upon the object must be zero. My experimental setup included a ball of 0.45 kilograms and a diameter of 0.2 meters. The ball was recorded at 30 frames per second with a total of 26 frames for the whole video. The orientation of the axes was that the positive x direction was towards the right of the video. For me to use Newton's second law, I must have an initial velocity as it will be the only factor that will calculate the final velocity under constant velocity conditions, meaning every point on my video should theoretically have a velocity equivalent to my initial velocity. I would have used my initial conditions to calculate my initial velocity, but seeing as how the position is 0 and the time is 0, which would imply that my object was at rest for the entire video, I used the average velocity, which I calculated by taking the difference of the final and initial positions over the difference of the final and initial times, which resulted in an average velocity of 0.970 meters per second in the x direction. Using the template code provided, I inputted the properties of the system, my ball, and the initial conditions as listed on the experimental slide. For the calculation loop, I inputted the data so that the while loop would apply Newton's second law to update both velocity and position for each timestamp that was less than my final timestamp of 0.867 seconds. Additionally, I placed a line of code before the while loop so that the code would plot my initial point of 0 meters in the x direction at 0 seconds on the position versus time curve. Plotting both data from my computational model and experimental model on one graph, I find that the two curves are highly similar with little variance between them. However, most of the variance comes from the time intervals in between 0.133 seconds and 0.8 seconds, where it was most noticeable that the experimental model strayed away from the computational model. The causes behind these discrepancies are that the manual input of the center of mass in the tracker program was not perfect, as I clicked on what I perceived as the center of the ball and not knowing if it was actually the center. Velocity in real life is rarely constant due to the unknown number of various forces that interact with my ball at various magnitudes, and additionally the ball not rolling in a linear path because what I perceived as the linear path could have been the ball traveling in any other axes other than the x direction. Now what if the orientation of the axes were altered so that the x-axis was flipped? In this scenario, what you are essentially doing is multiplying -1 to the initial velocity in Newton's second law, which would cause all the resulting velocities to take on the opposite direction. And the graph displays this by having the positions in the x direction taking on a negative value while having the same magnitude and time intervals. Now what this all means is that constant velocity can be achieved by having a net force equaling 0. And while it is not simple for me to identify all the forces that are acting upon the ball, I can assume that there are 5 main forces acting on the ball with their total sums of pushes and pulls equaling to 0. The main vertical forces that I assume that are interacting with the ball are that of the downward force of gravity and the upward force exerted by the floor, having their sum equaling 0, and the main horizontal forces that I will assume are the driving force that propels the ball in the positive x direction against the air resistance and friction, and their net force also equaling 0, which implies that the net force acting upon the system, the ball, is equal to 0, causing it to move in constant velocity.